Hi, this is the video for section 5.2 of A Student's Guide to the Schrödinger Equation. This one's about the finite rectangular potential well. And as it says here in the first paragraph, this has some similarities to the infinite potential well, the main being its piecewise constant potential. So you see there's the well region, which has zero potential energy all across it. But now outside the well, instead of infinite potential energy, the potential energy is V0. Still constant, but not infinitely big. And that's going to have an impact on the wave function solutions to the Schrödinger equation. I'll also point out that for reasons of symmetry, we've set the middle of the well to x equals 0, so the well still has width little a, but it goes from minus little a over 2 to positive little a over 2. There's a footnote here that in some quantum texts, they'll take the v equals 0 level to be the region outside the well, and they'll write v equals minus v0 here at the bottom of the well. But remember, it's only the change in potential energy that matters, and in both cases, the difference between the top and the bottom of the well, that is v top minus v bottom, is v0 in both cases. And as it says in this paragraph, there are some similarities between the infinite rectangular potential well and this finite rectangular potential well, one of them being that wave function will be oscillatory within the well. Also, the value of the wave function must be continuous across the boundaries. That is, just inside and just outside the well, the wave functions must match. Remember, in this case, those are at positions x equals minus a over 2 and x equals a over 2. However, there are some differences. As I said, the wave function will not be required to have zero amplitude outside the well, and in this case we're going to enforce the boundary condition that the slope must be continuous across the walls. So given that we've got conditions for continuous psi and continuous partial of psi with respect to x, we're going to get a somewhat more complicated equation in order to calculate our allowed energy levels in the wave functions, but you're going to see how to solve that equation in this section. Another important difference is in the finite well, particles may be bound or free depending on their energy and the characteristics of the well. So if E, the particle's total energy, is less than V0, the particle's bound. But if E is greater than V0, the particle is not bound in the well. In this section, we're going to deal with the bound case. So we're going to take the particle's energy E to be between 0 and V0. So what does that mean about the region outside the well? Well, if you read chapter 4, you probably know that even though the wave functions are oscillatory inside the well, since they don't go to 0 at the edges, they will exist outside the well. But in that region, they will decay exponentially, and I tend to call that the evanescent region. Another similarity to the infinite well is that the energies of the particles in the finite well are quantized. That means they can only take on certain allowed values. Now you may remember in the infinite well, there was an infinite number of allowed energy levels. That's not true in this case. The number of energy levels that are allowed depends on the width and the depth of the well. By depth, I mean the difference of potential energy inside and outside. So we'll talk about why the energy levels are discrete in the finite potential well, and we'll talk about some of the variables that are used in quantum texts, which can get a little daunting in solving the equation that arises from the boundary conditions. If you haven't read section 4.3, I think that's probably a good idea to do that before you go through this section, because in that section there's a curvature analysis that talks about what happens when the total energy E of the particle is greater than or less than the potential energy V in the region. We talked about the classically forbidden regions where E is less than V and the exponentially decaying behavior there. But inside the well, V equals 0, so as long as E is greater than 0, you will get the sinusoidal oscillating behavior of the wave functions. That looks exactly like it did in the infinite well case, where once again, since V equals 0 inside the well, we just have curvature term equaling these constants times the separation variable E times the wave function psi, and we group these into a variable we call k squared. That makes k this, just as you've seen before. One difference in the treatment in this section is that when we're solving the Schrödinger equation, we can use either exponentials or sinusoidal functions, and we used exponentials in the case of the infinite well. But remember, in section 5.1 I mentioned that as long as the potential energy function v of x is symmetric about some point, such as the middle of the well in this case, the solutions will have either even or odd parity. And that's very helpful in the case of the finite well. So sinusoidal functions are somewhat easier to work with, and therefore we're going to write the general solution as this. As I mentioned in the previous section, this is precisely equivalent to writing it with exponentials. It's just going to be a little easier to apply parity in this case. As before, k represents the wave number, and that determines the wavelength through k is equal to 2 pi over lambda, and therefore the larger the total energy E, the faster the particle's wave function will oscillate with distance in the finite rectangular well. Remember, when we say faster in this case, we mean faster over distance. Okay, but what about outside the well? To the left and right of the potential well. In those regions, we write the Schrödinger equation like this, just as we did before, and now our kappa looks like this. Remember, this was infinity in the infinite potential well case, so we just said kappa was infinitely large. That's not true here. Kappa depends upon the difference between V0 and the particle's energy E. But, as we said in Chapter 4 and in the previous section, kappa is a decay constant. It determines the rate at which the wave function tends towards 0 in the classically forbidden region. Since that's proportional to V0 minus E, the bigger that difference, the faster the waveform will decay to 0. That's why in the infinite well case, when V0 is infinity, it decayed infinitely quickly. That is, it went to 0 at the boundaries. Now, it's going to go to 0 over some range of distance outside the well. So we're going to write our general solution just as we did before, and recall, with kappa infinitely large, we had to set both of these constants to 0, and that meant no waveform outside the well. Not true now. So what can we say about the constants? Well, there's a little description in this paragraph that takes advantage of that parity consideration I mentioned. If you notice, region 1 is the region to the left of the well, and region 3 is the region to the right of the well. And in region 1, where x is less than minus a over 2, that means x is negative. And if x is negative, this term is going to blow up as x approaches minus infinity. Calling the d coefficient d left in that case, we got to set d left equal to 0. In that region, this term's okay because x is negative, and so this term will not blow up. If we go to x equals negative infinity, this term will go to 0. Okay, what about in the right region? That is region 3. I'll clean this up so you can see it better. Calling those constants in region 3 c right and d right, in that region x is positive. So as x goes to infinity, this term is going to blow up. So there, we got to take c right as 0, and only this term can be non-zero. So that means in region 1 to the left of the well, psi of x is c left e to the kappa x, because x is negative there. And in region 3 to the right of the well, psi of x equals d right e to the minus kappa x. That's where x is positive. Now we invoke the symmetry. Because the potential is symmetric about x equals 0, the wave function psi of x must have either even or odd parity across all values of x. That means inside and outside the well. Well, having parity means it can either be even or it can be odd. In the even case, it's got to be the same in region 1 as in region 3, and that means c left must equal d right. But if it's odd, then the sign of the wave function must be opposite in region 1 and region 3, and in that case, c left must equal minus d right. So we're going to write for even solutions that c left equals d right. We're just going to call that c. And for odd solutions, we're going to write that c left equals c and d right equals minus c. Here's a table in which we show it. This is just the inside the well, the oscillatory region. We can have either a cosine kx or b sine kx, in which cosine is even and sine is odd about the center of the well. But in regions 1 and 3 outside the well, in the even case, we have c e to the kappa x and c e to the minus kappa x, and in the odd case, c e to the kappa x and minus c e to the minus kappa x. Notice that in the same table, I've also shown the partial derivative of psi with respect to x. That's given by this in the left evanescent region, given by this in the right evanescent region. And when you take the derivative of the oscillatory, the cosine becomes a minus sine, brings a k out. The sine becomes a cosine, and it brings a k out as well. Why did I write those? Because both the wave function and its slope must be continuous across the boundaries. So now we're ready to apply that. We can apply it at x equals minus a over 2 and at the right edge at x equals a over 2. Let's just match the wave function at minus a over 2. I've plugged in minus a over 2 for x here and set those equal to each other. Now we take the slope at the left wall and again plug in x equals minus a over 2 in each case. And here's the trick. We now divide this equation by this equation. Why do we do that? It's going to simplify things. Lots going to cancel. Look at this. These c's cancel, these terms cancel, these a's cancel, and sine over cosine becomes tangent. So we get that kappa equals minus k times tangent of minus ka over 2. Or, pulling this sign out and canceling that one, kappa equals k tangent ka over 2. If we divide through by k, it looks like this. So look at what we've got here. This is a constant describing the rate of decay outside the well, and this is a constant determining the curvature inside the well. That ratio must equal the tangent of Ka over 2. We'll talk about solving that in a minute, but before getting to that, take a look at this paragraph. It asks you to step back and remember what the time-independent Schrödinger equation tells you. It says the constant kappa determines the curvature, that is the decay rate, of psi of x in the regions 1 and 3 outside the well. But we also know that kappa is proportional to the square root of v0 minus e. Now what is v0 minus e? Let's go back and look at our drawing of the well. Say the particle's energy E is right here. What is v0 minus e? Well, v0 is this level. Here's e. v0 minus e is how deep in the well, if you will, the particle's energy is. So if v0 minus e is a small number, particle's energy is up here. If v0 minus e is a big number, the particle's energy is down here. So I think of v0 minus e as giving an indication of how deep in the well the particle is. And remember, depth here refers to the energy, not the position of the particle. You see I use the phrase depth of the particle's energy level in the well. Okay, what about K? K, we said, determines the curvature and therefore the oscillation rate in the oscillating region, that is inside the well. But we know that K is proportional to the square root of energy E. So what does E tell you about where the particle is in the well? Back up to our picture. E tells you how far above the bottom of the well the particle's energy is. So the higher up the particle, the bigger K gets. And the smaller E, the closer to the bottom of the well the particle is, and the smaller K gets. So I call that the height of the particle's energy level in the well. And finally, a little paragraph here giving what I call the payoff of this logic. There are only certain values of energy, that is certain ratios of the depth to the height, that will cause both psi and its first derivative to be continuous across the boundaries. For example, if we're down here, we're low in the well. That means low curvature within the well. Pretty flat line there. But since we're far from the top of the well, that means steep curvature in the evanescent region. So this slope doesn't match that slope. What if the particle's energy is up here? Now, inside the well, since E is pretty big compared to 0, the slope is pretty steep, but outside the well, since v0 minus e, which is the distance from the top, is getting smaller, there's a lower slope, lower curvature there. And only at certain values of energy, that is certain distances above the bottom and below the top of the well, does the curvature in here exactly match the curvature outside the well. That is an allowed energy level. This one's not, because the slopes don't match. This one's not. This is critical to understanding the finite potential well, so if you don't get that, read that paragraph again. You may say, okay, I'd rather just look at the equation. Fine, but be aware, this is a transcendental equation. That means it involves trigonometric functions, and you cannot solve it analytically. You can solve it with trial and error, but we're going to do a little better than that. We're going to use a graphical approach, and you can see that on the next page. If you're not familiar with graphical solution techniques, or if it's been a while since you've seen one, I've got a very simple example here. Here's a transcendental equation which says that x over 4 equals cosine of x, which you cannot solve analytically. But to solve it graphically, you simply plot both sides of the equation on the same set of axes. So we're going to make our horizontal axis x, and we're going to make our vertical axis, if you will, the y dimension. First, we're going to set y equal to x over 4 and plot that. You can see that's this dashed line right there. Then we're going to make y equals cosine of x. You can see that plotted with the solid curve there. From there on, it's a pretty straightforward matter to find where do these curves intersect. And over this range, in 3 places. At each of those locations, x over 4 must equal cosine x. So you simply drop down to the x-axis and read off the value. Drop down to the x-axis, read off the second value. Drop down to the x-axis, read off the third value. So quite straightforward for a simple equation like this. As it says here, a little more complicated for the transcendental equation we have, in which kappa over k equals tangent of ka over 2. But the technique is exactly the same. As it also says here, in most quantum books at this point they introduce a substitution of variables in order to simplify the appearance of the terms in the equation, but I think it's a little more understandable if we actually use a real example for this, so I've included numbers in this graph. And you can see the graphical solution here. I make the horizontal axis Ka over 2. As you'll see in a bit, that's actually related to energy, but I'm calling it that because K appears in both the kappa over K side of the equation and in the tangent Ka over 2 side of the equation. The dashed curves, here, here, and here, are the tangent of Ka over 2. The solid curves, which you see starting up here and coming down and to the right, are the kappa over K curves. And I've selected some specific values here. For example, the width of the well, I've made 2.5 times 10 to the minus 10th meters, and I picked 3 values of potential energy V0, 2, 60, and 160 electron volts. Here you see the curve for V0 equals 2 eV, here's the one for V0 equals 60 eV, and here's the one for V0 equals 160 eV. And right away, you spot some places where kappa over K equals tangent Ka over 2. For the 2 eV case, there's one intersection of the curves right there. For the 60 eV potential well, there's a solution there and a solution there. And for the 160 eV well, there's 3. One there, one there, one there. Now you may be wondering, why are these curves shifting up and to the right for larger V0? Remember that kappa is proportional to the square root of V0 minus E. So as we make V0 bigger, kappa gets bigger. And kappa is in the numerator of the kappa over K term, so that's why the 160 EV curve is above the 60 and 2 EV curves. And where is energy in all this? Well, remember, K is proportional to the square root of the particle's energy. So therefore, as Ka over 2 increases to the right, those represent higher energies. And as it says here, since K is in the denominator of kappa over K, as Ka increases to the right, the curves move downward. That's why they have the shape they do as Ka over 2 increases. So it's summarized here. The wave number K is proportional to the square root of energy E, so the range of Ka over 2 is equivalent to a range of energies. We're looking for those energies at which kappa over K equals tangent of Ka over 2. That's where the wave function psi and its slope are continuous across the edges of the well. We're going to turn those Ka over 2 values into energies, but first I make the point here that for the even wave functions we're looking at in this graph, there are 3 solutions at 160 eV, 2 allowed energies at 60 eV, and only 1 at 2 eV. So in general, deeper wells may support more allowed energy levels. But I try to be really careful and use the word may here because you have to understand that if you just increase the depth of the well, let's say from 2 eV to 3 eV, that would be another curve there, you wouldn't get any additional solutions. Why not? Because in order to get another solution, you have to hit this next tangent Ka over 2 curve. So just increasing the well depth a little bit isn't going to do it. Only when we increase it enough that we get another intersection is there going to be another solution. Likewise, at 60 eV we got 2 solutions. At 70 we still would only have 2. But by the time we get to 160, we're intersecting this third tangent Ka over 2 curve, so we do get another solution. So it says, in general, deeper wells support more allowed energies. After all, the infinite potential well had an infinite number of allowed energies. But the only way to know how many solutions there are, that is, how many energy levels in a given well form acceptable solutions, is to solve the transcendental equation, and don't forget to use both even parity and odd parity solutions to the Schrödinger equation. So let's figure out what our range of energies is over the Ka values that we've got on the horizontal axis of the plot. Here's the equation relating energy to K. If we solve that for energy, we get this. But we're plotting Ka over 2 on the horizontal axis, so it's helpful to do this little trick. Notice what I've done is I deliberately introduced a Ka over 2 squared and a 2 over a squared term, which is just K squared when you multiply them together, but in this way we can see Ka over 2 squared as a separate term. That way, when we get a value for Ka over 2, we can plug it in here and determine the value of energy. For example, the plot goes from roughly 0 to 3 pi. Let's see what that corresponds to. We know that at 0, E is 0, but at 3 pi, I plug 3 pi in here for Ka over 2, crunch the math, and we get about 216.6 eV at the maximum of our horizontal axis. Now we're ready to read off our solutions. So we'll take the 160 eV case. There's one solution, drop down. We get Ka over 2 is equal to 0.445. If we then convert that to energy, we find out it's equivalent to 4.76 eV. Next solution, drop down. Ka over 2 is 1.33 pi. That's 42.4 eV. And the third solution, 2.18 pi for Ka over 2, 114 eV for E. So do those make sense? Well, what I do here is I compare them to the energy levels of the infinite potential well. The wells have the same width, and I've used the mass of the electron for both. Plug those values in, and here's what we get. The superscript infinity here means these are the energy levels for a particle with this mass in a well of this width. And since we're only doing the even energy levels in the finite well, we're going to compare them to E1, E3, and E5. Why the odd ones? Well, the lowest energy level is an even solution in the finite well, and the lowest energy level is called E1 in the infinite well. So these odd indices turn out to give us the even solutions. Remember, even and odd solutions alternate. So we're going to compare these three to our three values that we found from the graph. And what we find is in each case, the finite well has slightly smaller energies. If you take the ratios of those, they range from about 0.8 to about 0.76 for those three values. So why should the energy levels of the finite well be smaller than those of the corresponding infinite well? I think the best way to think about that is to look at the wave functions. Back here in figure 5.10, remember only this one is an allowed wave function because the slopes match at the boundaries. But notice, the curvature of this wave function is such that it hasn't gotten back to 0 yet because, unlike the infinite well, the wave function outside the well is not 0. So we don't have to go all the way down to 0 at the edges here. That means the curvature can be slightly less than the curvature of the infinite well, where we had to get back to 0 in this first lowest energy half cycle case. So that means that the wavelength can actually be a little longer. And if the wavelength is a little longer, that means K is a little smaller. Remember, it's 2 pi over lambda. And if K is a little smaller, the energy is a little smaller. So since the finite well wave functions don't have to be 0 at the edges, they can have slightly longer wavelengths. That's described in here. And then I point out, you should also remember, there's another very important difference. A finite potential well has a finite number of allowed energy levels, unlike the infinite potential well, which has an infinite number of allowed energy levels. As we're going to see, every finite potential well has at least one allowed energy, but the total number depends on both the depth and the width of the well. So, we've looked at what changing the depth of the well, that is V0, 260, 160 eV. But they all had the same width. A was 2.5 times 10 to the minus 10th meters. What if we vary that? You can see that in this figure. Same Ka over 2, but now I've picked V0 to be just 2 eV. And these three k over kappa curves correspond to different widths. 2.5 times 10 to the minus 10th meters, as before, 10 times 10 to the minus 10th meters, and 25 times 10 to the minus 10th meters. So what happens as the well gets wider? You get more solutions. Maybe. Once again, you've got to make it enough wider that you hit the next tangent Ka over 2 curve. The one I just drew would not get us any additional solutions. But if you increase it enough, the width of the well I'm talking about, you do get another solution. So the same caveat applies, which is, in general, wider wells mean more solutions, but you cannot guarantee that widening the well a little bit will get you another solution. You have to solve the transcendental equation to know that. We're going to talk about the odd parity solutions as well in just a minute, but first I think it's worth a little of your time to consider an alternative form of the even parity solution that you may run into in a comprehensive quantum book. And to see that form, start by taking our transcendental equation and multiplying both sides by Ka over 2. Notice on the left side that means this K will cancel, and you'll be left with A over 2 times kappa. And the right side is just the tangent, Ka over 2 scaled by Ka over 2. The effect of this change is shown in this figure. First of all, notice the dashed lines represent the tangent Ka over 2 as they did before, but now they're scaled by Ka over 2, so they're slightly modified. But the much bigger change comes about for the term that used to be kappa over K, that is now A over 2 times kappa. And look at what those are. It's a little hard to see this one down here. It's a circle. So is this one, so is this one. And those, as before, represent V0 is 2 eV, 60 eV, and 160 eV. The solutions are still given by the intersections, but why are these circles? To understand that, remember that K is proportional to the square root of E, and when we solve that for E, we got this, which explicitly includes the Ka over 2 that we have as our horizontal axis. And now we need to define what I call a reference wave number, K0. If the particle's total energy were V0, that is, if it were right at the top of the well, energetically speaking, then the wave number, which I've called K0, would be proportional to the square root of V0. And solving that for V0, we come up with another expression in terms of this wave number, kappa 0. It's not the wave number the particle has, it's the wave number it would have if its energy put it at the top of the well. The reason for defining that is our equation for kappa involves both V0 and E. So we're going to plug in our expression for E from up here and our expression for V0 in here, and look at what we get. Okay, it looks kind of messy, but you can see, for example, this h bar squared term cancels out there. This m goes away with that m. These 2's multiply to give us 4. The a squared is still there. But look at this. We get K0a over 2 quantity squared minus Ka over 2 quantity squared. So when we multiply that by a over 2, that moves inside and cancels this 4 over a squared, and we just get this. So is that a circle? Absolutely. To see that, remember the equation of a circle on an xy plot is x squared plus y squared equals r squared, where r is the radius of the circle, or if you solve for y is the square root of r squared minus x squared. Well, we're plotting a over 2 times kappa on the y-axis of our graph. We've got the square root, and our x-axis is Ka over 2. So that means that these are going to be circles with radius K0a over 2. Again, we got that because we plotted a over 2 kappa on the y-axis and Ka over 2 on the x-axis. So now let's look at that again, clean it up a little bit, and sure enough, a over 2 times kappa are circles about the origin. And exactly as we saw in the other form, we have one solution for V0 is 2 eV, 2 solutions for 60 eV, and 3 solutions for 160 eV. So this form of the plot is going to give us the exact same answers. It's just going to be a little more useful when we introduce the change of variables that many quantum books use. That's explained here, and we'll get to that substitution of variables after we find the odd parity solutions. So how are we going to do that? The same process we used for the even solution case. Start by looking back on our table of solutions within and outside the well. Here's our table. I've written all over it, so I'll clean it up. So now we're going to use this odd solution, b sine kx, for which the slope is kb cosine kx. At the left edge of the well, there's the equation for continuity. That is, this is outside the well, this is inside, and here's the slope, that is the derivative of those, outside and inside. And just as we did before, we're going to divide this equation by this one. That's shown down here. Exactly as before, the c's cancel, this cancels, the b's cancel, and cosine over sine is cotangent. So you see that written there. There's the kappa, there's the k. Since we've got a minus sign inside, we can move that out, and we get minus k cotangent k over a. If we divide both sides by k, this is the odd parity version of the transcendental equation that we saw earlier for the even parity case. The only difference is where we had a positive tangent, we now have a negative cotangent. So what does that look like when you plot it? Well, the kappa over k terms are the same. I took the same three values of 2, 60, and 160 EV, but the minus cotangent functions are now these. And notice, they're shifted over along the k over 2 axis in a way that's going to make a difference. Why? Well, for one thing, look at the 2 EV case. It doesn't intersect any of the minus cotangent ka over 2 curves. That means no solutions for the 2 EV well. And for the 60 EV case, there are 2 solutions. For the 160, there are 3 solutions. You can also use the other form of the plot where we multiply both sides by k over 2. Now we see our little circle for the 2 EV case does not intersect any of the minus cotangent curves. But our 60 EV case intersects at 2 places and our 160 at 3, exactly as in the other plot. So as it says here, that's one consequence of having those negative cotangent curves shifted over by pi over 2 to the right. So in the even parity case, since they started at the origin, we're guaranteed to have at least one solution. I can show that here. Remember, the even parity case looked like that. This one starts at the origin. We're always going to have at least one intersection. Not true for the negative cotangent curves. So it says here, it is possible for a shallow, that is small v0, and narrow, that is small width a, well, to have the kappa over k curve get down to kappa equals 0 without ever crossing one of the negative cotangent curves. So that's the graphical explanation of why there are no solutions. What's really going on physically that says there's always going to be at least one even parity solution, but maybe no odd parity solution if we have a sufficiently narrow and shallow potential well? Here's how I think of that. Here's a relatively shallow potential well, 2 EV. I've drawn the line down the middle at x equals 0 so we can see that in this case, this is an even parity function. It's the same on both sides of the dashed line. This is an odd parity function. It's got to have opposite sign to the right of the dashed line and the left of the dashed line. I picked positive on the right, negative on the left. You could have gone the other way. But we know that at the boundaries, the slope of the wave function within the well must match the slope of the wave function outside the well. But this well is only 2 EV deep. That means that for a particle to be bound in the well, its energy cannot exceed 2 EV. It's got to have small e. And remember, the curvature is proportional to the energy. So small energy means small curvature. Well, in the even function case, we can have low curvature. It means this is relatively flat in here. And in the evanescent region, the curvature is proportional to the square root of V0 minus E. So there will always be some E between 0 and V0 that has just the right difference from V0 to set the curvature in the evanescent region so that the slope matches the slope on the other side of the boundary. But in the odd case, if this is very flat in the evanescent region, it's got to match that slope within the well. If it's reasonably flat at the boundary, it's got to go through 0 because it's got to have an opposite sign on the right side and the left side. So it's got to have enough curvature to go through 0 and then flatten out at the top. But there might not be room for that function to go from flat through 0 and get to flat again. As it says here, the small curvature due to the low value of V means that the odd parity wave function doesn't have room to turn over, to go from minus to plus or plus to minus at the center of the well and be flat at the edges of the well. So if the well is too shallow and too narrow, you may have no hope of matching the slope and therefore no solutions. That's the case for a 2 EV finite rectangular well with this width. So if I increase the width of the well, might we get solutions? You can see that in this figure. All of these curves are for V0 is 2 EV, but if I increase the width of the well to 10 times 10 to the minus 10th, this curve moves up and to the right, and I pick up a solution. If I increase it more to 25 times 10 to the minus 10th, there are actually 3 solutions. So if I had made the well deeper but still shallow, I could have gotten solutions. Likewise, if I make the well wider, even at the shallow depth, I can get solutions. But if the well is what we call a small or a weak potential well, by that we mean shallow or narrow, it may not support any odd parity solutions, although there will always be at least one even parity solution. So you can think of the odd parity solution not occurring as the kappa over k curve not intersecting the negative cotangent curve, or you can think of it as the slope of the odd wave function at the inside edges of the well not being able to match the slope of the decaying wave function outside the well. Either of those perspectives is valid. Okay, if you dig off the values of Ka over 2 for these solutions, here's what you get for the 160 EV case, and here are the allowed energies. If you compare those to the infinite potential well, now we compare them to E2, E4, and E6 for the reasons I explained earlier, and you'll see that the finite well's energies are 70 to 80%, exactly as they were in the even case. You can see those wave functions in figure 520. So you can see that the wave functions alternate between even and odd, and for the lowest energy state, the wave number k has the smallest value, and the curvature is also the smallest. But there has to be enough curvature to match up the slope of the waveform to the slope outside the well, and there the curvature is provided by the value of v minus e, which has the largest value for this lowest energy waveform, and that means the decay is fastest down here. As we go up in energy, k increases, so the curvature gets greater and greater. That means more cycles within the well, but it also means smaller and smaller V0 minus E, and that means less and less steep curvature in the evanescent region, and therefore farther penetration into the classically forbidden region. That's described in this paragraph. So the last thing we do here for the finite potential well is this substitution of variables that I mentioned earlier that you're going to see in lots of comprehensive quantum texts. And to understand that substitution, start out with a variable called z, which we're going to define as Ka over 2. So what does that mean? Well, we know what the wave number k is. It's 2 pi over lambda. So if we multiply k by a over 2, we can think of that as 2 pi times a over 2 over lambda. And what does that mean? Well, this term just tells you how many wavelengths there are in the half width of the well, a over 2. And whereas this term gives you the number of wavelengths in the half width of the well, by multiplying by 2 pi, we turn that into radians, where 2 pi radians represents one complete wavelength. So if z has a value of 2 pi radians, we have one wavelength in the half width of the well. If z has a value of 4 pi radians, we have 2 wavelengths in the half width of the well, and so on. So that's all there is to z. But it's going to be helpful to see how it's related to energy. Remember, k is related to energy, so if I take Ka over 2, which is the definition of z, and plug in square root of 2m over h bar squared e for k, I get this expression, and if you solve that for e looks like these constants times z squared. We'll use that in a minute. But for now, look at our even solution transcendental equation, which said kappa over k is tangent of Ka over 2. If for k, we plug in 2 over a times z, that's from up here, and since z is Ka over 2, we just have tangent z, so this is now our even solutions transcendental equation. But that doesn't look particularly helpful, so at this point we define another variable we call z0. That variable is the product of k0, Remember the reference wave number k0 times a over 2. And what is k0? We said it's the wave number of a quantum particle whose energy is equal to the depth of the well, that is V0. So essentially a particle that is right at the top of the well energy-wise. Z0 tells you how many wavelengths for that particle fit in the half-width of the well, once again converted to radians. And just as we did before, we can substitute in for k0 an expression involving v0, and then when we solve that for v0, we get v0, same constants as we had in the E case, and now we've got a z0 squared. Why have we done all this? Remember what kappa is. Kappa is this expression, and it's got a v0 and it's got an e. So we're going to grab our e from up here and our v0 from here and plug them in down here. When we plug those in, we get this thing, and doing a little canceling, and the h bar squareds, we get this. Or if we pull the 4 over a squared outside the square root, we get this. Now look at what happens when you take kappa over k, which as I said is 2 over a times z. That means we take this guy divided by 2 over a times z and set that equal to tangent of z. When we cancel these 2 over a's and bring z up inside, it looks like this. So we've turned our even solution transcendental equation into this. And that's a version you are very likely to see in other quantum texts. So when you look at it, just remember, Z is a measure of the total energy of the particle, and Z0 is related to the depth of the well, V0. So if you have a given well and a particle of a certain mass, higher energy means larger Z, and deeper well means larger Z0. Once you have that expression, the graphical solution process is exactly what we've seen before, as you can see in figure 521. Now, instead of kappa over k, we're plotting square root of z0 squared over z squared minus 1. We've got tangent z, which is tangent ka over 2, just as we had before. The horizontal axis is z, which is ka over 2, as it was before. And our tangent z curves are just the same. So I've picked 3 values of z0. One has z0 equal to 1, one has z0 equal to 5, and one has z0 equal to 8. And just as in the even function case before, there is one solution for z0 equals 1, 2 solutions for z0 equals 5, and 3 solutions for z0 equals 8. If you're wondering why I used 1, 5, and 8 for z0, solve this equation for v0 using these values for z0. When you plug in modified Planck's constant, width of the well, mass of the particle, plug in all those, and for z0, I'll do the case of z0 equals 1 here, you get 2.4 eV. And remember, the shallowest well that I used before was 2 eV. When you set 0 equal to 5, that's equivalent to v0 of 61 eV, and z0 equals 8 corresponds to 156.1 eV. In other words, z0 of 1, 5, and 8 come close to the v0 values of 2, 60, and 160 eV that we used before. Don't take from this that z0 is restricted to integer values. Had I used these precise values, I would have gotten exactly 2, 60, and 160 eV for v0. So plotting in z gives you the same answers as plotting in kappa over k. And just as in the previous case, you can get an alternative version, you can here too by multiplying both sides by z. There's a z, there's a z, and when you incorporate this z inside, you get this expression. I call this the z version of the expression we had previously when we multiplied both sides by ka over 2. And you know what the z version of this looks like? Exactly what you'd expect. Now we have these circles for z0 squared minus z squared, exactly like we said, y is equal to the square root of r squared minus x squared. So the radius of our circle is going to be z0, and the x-axis is going to be z. So this is the z version of the alternative graphical solution for the even case, just as we had before. You can use whichever version you prefer. You can use this exact same approach for the odd parity solutions. Guess what's different? Instead of tangent of z, we have minus cotangent of z, exactly as we had previously. When you do that, here are the odd solutions. Notice, for z0 equals 1, no solutions at all, no intersections with the negative cotangent curve. For z0 equals 5, 2 solutions. For z0 equals 8, 3 solutions. And if you multiply through by z, you get the alternative expression, and you can see those graphical solutions right here. So, doing this z substitution does not change the physics in the least. It just reduces the complexity of the appearance of the equation, but it's important that you remember what those variables represent. Final paragraph of this section says, the finite potential well has turned out to be a little more complicated than the infinite well in terms of finding the allowed energies. But it is, of course, a little more realistic in that we don't have infinite potential energies, although it does still use piecewise constant potentials, which means that there's zero force acting on the particle within the well, and it would be nice to have an example in which the force in the well is not zero. That means that the potential energy is not constant. And the last section of this chapter has exactly that. In that section, you're going to find potential energy not constant. The force is non-zero because we're going to be dealing with the quantum harmonic oscillator.